Good morning. Today's lesson is on recursion. It's your introduction to recursion. We're actually doing recursion with another unit. Unit 4 is on recursion in models, and Unit 5 is on function in models, and they kind of go hand in hand. We are accustomed to functions. We are not accustomed to recursion, so we'll get on it. So let's look at this bell ringer. Bell ringer says, what is the eighth term in this series? We're doing 1, minus 2, 4, minus 8, 16, and what is the eighth term? We're going through 5 terms. So the first thing we need to do is, what is happening to the terms when the next sequential number shows up? So the first number is 1, the next number is minus 2. So what do we do to 1 to get to minus 2? We could have subtracted 3, but then the next number, we're adding 6. And then the next number, we're subtracting 12. And the next number, we're adding 24. So that doesn't seem right. It seems like something else is going on. What is common? What if we multiplied 1 by minus 2? That would give us minus 2. And what if we multiplied minus 2 by minus 2? That would give us 4. Multiplying minus 2 by 4, we get minus 8. And we multiply minus 8 by minus 2, we get 16. So if that's the case, now we see a good sequence. The common ratio here, the common number that's multiplied by the number before to find the next number is minus 2. So if we multiply 16 by minus 2, that gives us minus 32. If we multiply minus 32 by minus 2, we get 64, right? So that's the 6th and 7th. We're looking for the 8th. Multiply 64 times minus 2, we get minus 128. And that, of course, is our 8th term. So we're looking at this sequence, and how did we determine what the next number in the sequence was? We looked at the last number, and we looked what we did to the last number to find the next number in the sequence. And that helps us determine it. Believe it or not, that is how computers work. They look at the last number to determine the next number. They don't even do multiplication in computers. They do a series of addition problems or a series of subtraction problems to determine exactly what's going on. And it's pretty cool the way it works. And it works at such a fast speed, it looks like they're multiplying in like we do in our head. So each term in the sequence is systematically determined by the previous term, multiplied it by minus 2 to calculate the next term. So, all right, good things. Let's see, what is my good thing? Checked our bees this weekend. We had really good activity. Our bees were actually picking up pollen. It was 70 degrees outside on Sunday, and so they were out foraging, and kind of looking forward to the spring flow and see what kind of honey we're going to get, and hopefully we'll split and get some more hives. So in the meantime, please be sure to share any good things you might have so we can share with the class. All right, so a sequence is a set of whose elements have an order. For example, the positive integers make up a sequence, 0, 1, 2, 3, 4. We're very accustomed to that sequence. All of the patterns you saw on day 1 of this unit were sequences, okay? And actually, we didn't do day 1, so it's kind of pointless to put that in there. Anyway, in mathematics, we generally consider a sequence to be a function whose domain is a set of consecutive integers. The values in this range are called the terms in the sequence. So if you see this little schematic down here, the domain is 1, 2, 3, 4, 5, 6, all the way up to the nth term. And by nth term, we talk about the limits of this function. N can be any number we can plug in. It can be the limit. It can be any number up to the where we want to stop at. And the range, we will use the variable a with subscript the number of the domain in it all the way up to a to the n. And that is what the term is. And we use this to help us determine exactly what the function is. All right, so consider the sequence 2, 4, 6, 8. What is the first term in the sequence, or a subscript 1? Let me back up. The first term in the sequence, obviously, is 1. What is the third term in the sequence? A3 is 3. Okay, well, we don't know. 2, 4, 6, 8. It's not 1. A1 is 2. That's the first term in the sequence. A subscript 3, or the third term of the sequence, is 6. The 7th term, we skip count and we can do it easy. Start with your fingers and you just count on your fingers. 2, 4, 6, 8, 10, 12, 14. The seventh term in the sequence is 14. Pretty simple mathematics if you think about it. Now, in the following three sequences, they all have something in common. What is it? 3, 7, 11, 15. Okay, how do we go from 3 to 7? I think we have something common there. Well, how do we go from 7 to 11? And how do we go from 11 to 15? They all have something in common. The difference between them is common. They have a common difference of 4. 3 plus 4 is 7. 7 plus 4 is 11. 11 plus 4 is 15, which means the next number in the sequence would be 15 plus 4, or 19. How about the number in the next sequence? 7, 2, minus 3, minus 8. In this one, it looks like we have a sequence that is going down. So they have a common difference. 7 to 2 is minus 5. 2 to minus 3 is minus 5. And minus 3 to minus 8 is minus 5. So the next number in the sequence would be minus 8, minus 5, or minus 13. In the last sequence, 2.4, 3.6, 4.8, and 6.0, what we're doing here, it looks like we're adding, it's not an integer, it's a number that's got a decimal attached to it. 2.4, 3.6, 4.8, 6.0. We're adding 1.2 to 2.4 to get 3.6. And I think we're adding 1.2 to 3.6 to get 4.8, 1.2 to 4.8 to get 6.0. So the next number in the sequence would be 6.0 plus 1.2, or 7.2. And these are called arithmetic sequences. And yes, I said arithmetic because that's the way you pronounce that. A sequence is arithmetic if each term has a common difference. The common difference of the first sequence is 4, so D equals 4. The common difference in the second sequence is minus 5, so D equals minus 5. And the common difference in the last sequence is 1.2, so D equals 1.2. And there you go. That's the explanation for it right there. Okay, identify whether each sequence is arithmetic. So minus 4 to 1, that is plus 5. 1 to 6, that is plus 5. 6 to 11, that is plus 5. And 11 to 16 is plus 5. They all have a common difference, so it's arithmetic. How about this next one? 3 plus 4 is 5. 5 plus 4 is 9. 9 plus 6 is 15. 15 plus 6 is 23. The first two sequence differences are the same, but the next two sequence differences are not. So we're looking at something that does not have a common difference. So the first one is arithmetic because it is a common difference of plus 5. The differences between each term changes for each term, therefore, is not arithmetic. Oh, and 3 plus 2 is 5. 5 plus 4 is 9. 9 plus 6 is 15, and 15 plus 8 is 23. I apologize, I didn't do it right. But you can see it's not arithmetic. The difference changes by 2 in every change of sequence. All right, so a sequence can be specified by an equation or rule. For example, the sequence in the first sequence can be described by the rule A subscript n equals 2 times n. Okay, so that's it. Whatever n is, say n is 5, the fifth number of the sequence is 2 times 5, or 10. The 10th number of the sequence, A subscript 10, is 2 times 10, or 20. And you can easily do that using your fingers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's the 20th number in the sequence. A subscript 20, or the 20th number in the sequence, is 2 times 10, or 20. How about this sequence with the rule A subscript n equals 3n plus 1? If we want to find the first term, that is finding A subscript 1, what does that mean n is? Well, if you're putting subscript 1 where the subscript n is, that means n in the function has to also be 1. So A subscript n, or A subscript 1, would be 3 times 1 plus 1, or 3 plus 1, or 4. Plug 1 in. Now, that's exactly what we're doing here. N is the number in the sequence. That is the term A subscript n is. A subscript 1 equals 3 times 1 plus 1, or 3 plus 1, which equals 4. What would we plug in to find the second term? N would be 2. Third term, n would be 3. The first 6 terms are this. A subscript 1 is 4. A subscript 2 is 7, 10, 13, 16, and 19. All we're doing is moving by 3, and that should be easily determined by this function of 3 times the variable n, which is the number in the sequence. But notice we're adding 1 to each one, so we don't actually start at 3, we start at 4. All right. Now, this is called an explicit formula for a sequence. The general form for the explicit formula of an arithmetic sequence that starts at 1 is a subscript n equals a subscript 1 plus the quantity n minus 1 times the variable d, where n represents the number in the sequence, a subscript 1 represents the first term in the sequence, a subscript n represents the next term in the sequence, and a subscript n minus 1 represents the previous term in the sequence. D represents the common difference. Okay, so let's move on. Consider this sequence rule. A subscript 1 equals 5, but a subscript n equals a subscript n minus 1 plus 4. So the first line of the rule tells you what the first term is. What is the first term in the sequence? Well, that tells you right there. We're given that answer. The first term in the sequence is a subscript 1, or 5. Suppose we want to find the second term. Well, if that is, what is the second term? Then what is n? N is 2. We'll plug that value into the second line of the rule. Okay, a subscript 2 equals a subscript 2 minus 1, or a subscript 1 plus 4. We're given a subscript 1, so we can put 5 in here for a subscript 1, since a subscript 2 minus 1 is 5. The answer for a subscript 2 is 5 plus 4, or 9. Now, do you see the A1 there? What is A1? Add 4 to that, and we have the second term, A2. Let's find the third term. Plug it in. We'll keep going until we have all the first 5 terms in the sequence. And we'll keep going until we get all 5 terms. That's easy. So if the first term is 5 and the second term is 9, we just keep adding 4. So the third term is 9 plus 4, or 13. The fourth term is 13 plus 4, or 17. And the fifth term is 17 plus 4, or 21. All right. So which method is the most convenient for finding the 10th term in the sequence? I would venture to say that the 10th term in the sequence would be easier to use it by plugging 10 in for n. So the explicit method would be easy. If we have something that has a value of n in there, and not just as a subscript, we wouldn't have to go through and reiterate or recurse the process 10 times to find the answer, which is how you have to do it for recursion. Which method is most convenient for finding the first 6 terms in the sequence? In that case, since you have to recurse to find them, it would be more efficient to just go term by term and find the first 6 terms. It makes it much easier that way than to multiply by the first 6 numbers or sequence, 1, 2, 3, 4, 5, 6, into a formula. All right. Consider the sequence 10, 7, 4, 1. What is the first term? A1. That is 10. What is the common difference? I think it's minus 3. What is an explicit and recursive formula for this sequence? Recursive, we're going to start with A1 is 10, and we'll, whatever the first term is, we'll subtract minus 3 from it. We'll subtract 3 from it, and then that gives us the next term. And then the next term after that is that minus 3. In explicit, we have to use a varied formula because we're using starting at 1 and not 0. A of n equals 10, that is A1, plus n minus 1 times minus 3. So we find out that A subscript n is 13 minus 3n. And you can check this if you like. So if you want to know the first term of the sequence, A subscript 1 is 13 minus 3 times 1, or 10. Second term of the sequence, A subscript 2, is 13 minus 3 times 2, or 6, or 7. So we're subtracting 3 every time. That's what the minus 3n is. All right. Now, recursion exists in a lot of places, and you may not have noticed this, and probably not many of you have gone sledding. I think when I did this video, or when I did the slideshow, it actually snowed in 2017. But anyway, this is how you go sledding. First, you got to get a sled. Then you find a snowy hill, climb to the top of the hill, sit on the top of your sled, ask someone to give you a sled, give your sled a push, sled down the hill. At the bottom of the hill, you got to get off the sled and go to the top of the hill to sled again and start the process over. That is called recursion. Okay, so that's the end of the lesson. Please go into the Google Classroom and get the assignment done as soon as possible. In the meantime, be blessed and be a blessing.